Tonight, the moon is 238,000 miles away. Tomorrow, a little further. It has been moving away from us for 4.5 billion years, at roughly the speed your fingernails grow, about 1.5 inches a year. Nobody notices, because nobody lives long enough to notice. But the moon has not always been where it is now, and it has not always looked the way it looks tonight. There was a time when it was 10 times closer, and it filled 1/3 of the sky, and it was glowing. There was a time before that when there was no moon at all. The moon is the only other world any human being has ever stood on. 12 people have done it, all of them between 1969 and 1972. And almost every date you are going to hear tonight was read out of the rocks they carried home. Here is what those rocks and the mirrors those astronauts left behind have told us. The moon is exactly the right size at exactly the right distance to cover the sun. That is the only reason total solar eclipses exist. It is a coincidence, and it is temporary. In roughly 600 million years, the moon will have drifted too far to cover the sun completely, and totality will begin to fail. First, occasionally, then never again. We are living inside the window when it still works. Tonight we are going to go through the whole of it, slowly and in order. 4.5 billion years from the collision that made it to the ice sitting in permanent darkness at its south pole. There is no hurry in any of this. The moon took 4.5 billion years to become what it is. It is not going anywhere in the next 3 hours. You do not need to stay awake for this. If you drift off somewhere in the first billion years, that is what this is for. It will still be here in the morning, and so will the moon. A few things to hold on to, gently, as we go. The moon is a little over 1/4 the width of the Earth, 2,159 miles across. It is old, very nearly as old as the Earth itself. It has no air, no weather, and almost no sound at all. And the far side, the half that never turns towards us, was not seen by anyone until 1959. Not glimpsed, not guessed at, simply unknown for the whole of human history until then. It is also the reason the sea moves. Twice a day, in every ocean on this planet, the water leans towards it and falls away again. And that slow, enormous dragging is the very thing pushing the moon further out. The tides and the departure are the same process running in opposite directions. The ocean is paying for the distance. It is probably also the reason the seasons are steady. Without a moon this large, the tilt of the Earth would wander, and the climate would wander with it. Whether that mattered for life is genuinely unsettled among the people who study it, and we will come to that argument later. We will come back to the leaving at the end. That is the thread. Everything in between is simply how it got here. But it does not begin with the moon. It begins with a young Earth spinning much too fast, with nothing in its sky at all. To find the beginning of the moon, you have to go back to a version of the Earth that would be unrecognizable to you, and then go back a little further than that. The solar system is 4,567,000,000 years old. That number is not a guess, and it does not come from any rock on Earth. It comes from meteorites, specifically from small white flecks inside them called calcium-aluminum inclusions, which are the oldest solid objects anyone has ever held. They condensed directly out of the cooling gas around the newborn sun, before there were planets to put them in. Every date in this documentary is measured against them. Before any of it, there was a cloud, a patch of gas and dust drifting in one arm of the Milky Way, cold enough that hydrogen molecules could survive in it and large enough that its own weight was slowly working against it. Something disturbed it, possibly the shock wave from a nearby star that had already died. The cloud began to fall inward on itself. As it fell, it spun. Anything collapsing under its own gravity spins faster as it shrinks, the same way a skater pulls their arms in, and the spin flattened the cloud into a disk. Most of the material went to the center and became the sun. What was left over, less than 1% of the whole, stayed spread out in that disk, and everything in the solar system was made from it. Every planet, every moon, every atom of you. We can watch this happening elsewhere, which is why we are confident about it. Radio telescopes in Chile have photographed disks around other young stars, complete with dark gaps where planets are already sweeping their orbits clean. What we are describing is not a reconstruction of something unrepeatable. It is a process that is running right now in thousands of places, and we have pictures of it. The Earth came together in the few tens of millions of years after that, not all at once and not gently. It grew like a snowball when it is rolled downhill by sweeping up everything on its path, and every one of those collisions arrived as heat. By the time it was roughly the size it is now, the outer few hundred miles of it were molten. There was no crust to speak of. There were no oceans because the surface was far too hot to hold liquid water anywhere. There was an atmosphere, but it was thick and heavy, and mostly steam and carbon dioxide, and it would have crushed you long before it suffocated you. And above all of it, nothing, an empty sky. That is the part worth sitting with for a moment. Every night sky any human being has ever looked at has had the moon in it, or has had the moon somewhere in it temporarily below the horizon and due back. It's the same object we all share. It's the same size for everyone, it keeps time for everyone, and it has been in every myth and every calendar and every love song ever written. And for the first 50 million years or so of this planet's existence, it simply was not there. Consider how much of ordinary human life is built on something that is, in the long view, a recent addition. The word month comes from the word moon in English and in most of the languages related to it. The Islamic calendar still runs on lunar months, and so does the Hebrew calendar, and so does the traditional Chinese one. Easter is set by the moon. So is the Chinese New Year. Sailors planned voyages around it, farmers planted by it, and for most of human history, if you needed to travel at night, the moon decided whether you could. None of that was available to the Earth for its first 50 million years, and none of it, as we will get to at the end, is permanent. We know almost nothing about that Earth directly because almost nothing of it survives. This is one of the quiet frustrations of the whole subject. The Earth is a restless planet. It melts its own surface, it folds it under, it grinds it down with rain and rivers and ice, and in doing so, it has erased nearly every trace of its own childhood. The oldest intact rock anyone has found on Earth is 4 billion years old, from the Akastic Gneiss in the Northwest Territories of Canada. That's already 500 million years after the Earth formed. 500 million years of history gone. There is one exception though, and it's a small and beautiful one. In the Jack Hills of Western Australia, embedded in much younger sandstone, there are grains of a mineral called zircon. Zircon is extraordinarily tough. It survives being melted out of one rock and buried in another, and washed down a river and cemented into a third. And it traps uranium as it crystallizes, which means it carries its own clock. The oldest of those grains is 4,404,000,000 years old. They're microscopic. You could lose one in the seam of your pocket. And the chemistry locked inside them suggests they formed in the presence of liquid water, which means the Earth had cooled far earlier than anyone used to think. That's a payoff worth having early. The Earth got cold, quickly. Not comfortable, but quickly. Now, the sky. If you had been standing on that early Earth, which you could not have, the sun would have looked wrong to you. It was about 30% fainter than it is now. Young stars of the sun's type burn cooler and brighten slowly over billions of years. And ours has been getting steadily warmer the entire time life has existed. The reason the early Earth was not a frozen ball, despite the faint sun, is that thick blanket of carbon dioxide. This is a real puzzle in the field, and it has a name: the faint young sun paradox. It is not fully solved. The days were short. After the collision we are building toward, the Earth was spinning so fast that a full day lasted somewhere around 5 hours. Sunrise, noon, sunset, and darkness, all inside the length of a modern night's sleep. Before the collision, we honestly do not know how fast it turned. That information was destroyed by the impact itself. It is worth pausing on what a 5-hour day actually does to a planet. Spin something that fast and it stops being a sphere. The Earth bulged hard at its equator, far more than the slight bulge it carries today. The winds would have been extraordinary because air moving from the equator toward the poles gets deflected by rotation, and the faster the rotation, the harder the deflection. Our modern weather systems are gentler by comparison. On a 5-hour Earth, storms would have been narrow, fast, and everywhere at once. And the stars would have been unfamiliar, not because the physics was different, but because the sun has since carried us more than 20 times around the center of the galaxy, and every constellation you can name has drifted apart and reformed many times over since then. The sky you would have seen had no patterns anyone has ever named. So, a hot young planet, spinning fast, wrapped in steam under a dim sun and unfamiliar stars, with nothing in orbit around it. Except that is not quite true. There was something else. The solar system at this stage was not the tidy place it is now. Today, we have 8 planets on well-separated, nearly circular tracks, and the arrangement looks permanent. It is not permanent. It is what's left over. In the beginning, there were dozens of bodies large enough to be called planets, jostling in overlapping orbits. Astronomers call them planetary embryos. They were moon-sized, Mars-sized, some larger, and they did not all fit. Over roughly 100 million years, they collided, merged, and threw each other out of the solar system entirely, until the survivors settled into orbits far enough apart to leave one another alone. Every rocky planet you know is the winner of that process. Mercury, Venus, Earth, Mars. Everything else lost. One of the bodies that lost was about the size of Mars, roughly half the diameter of the Earth, around 1/10 of its mass. We've given it a name, though nobody has ever seen it and nothing of it exists in recognizable form. It is called Theia, after the Greek Titan who is the mother of Selene, the moon. The name was proposed by the geochemist Alex Halliday, and it is a good one because it says exactly what the object was for. Where Theia came from is one of the genuinely open questions. One idea, and it's a strong one, is that it didn't come from far away at all. It may have formed in almost the same orbit as the Earth, sitting in one of the gravitationally stable points ahead of or behind us, slowly accumulating material for tens of millions of years, while our planet did the same. If that's right, Theia and the Earth were built out of the same batch of raw material, from the same part of the disk, at the same time. 2 planets from one recipe. Hold on to that. It matters enormously in the next section, and it's the reason the whole story nearly fell apart in the 1970s. Stable points like that are stable, but they're not permanently stable. Once an object grows past a certain mass, roughly what Theia had reached, the balance fails. Jupiter tugs, Venus tugs, the orbit begins to wander. And it wandered inward onto a track that crossed our own. There would have been no warning of any kind, because there was nobody to warn and nothing to notice. The 2 objects would have approached each other slowly by any human standard over thousands of orbits, each pass a little closer than the last. And then, 4.5 billion years ago, they touched. Nothing about the Earth after that moment was the same. Not its rotation, not its tilt, not its chemistry, and not from then on its sky. The collision that made the moon was not an explosion. It is drawn that way in almost every illustration, and the illustrations are misleading. 2 objects that size do not explode. They merge slowly, in a way that would have looked almost gentle if you could have watched it from far enough away. Theia came in at an angle, not head-on, which matters enormously, but a glancing blow of roughly 45 degrees at a speed of a few miles per second. Fast by any human measure, slow by the standards of things that hit planets. The 2 bodies did not bounce. At that scale, rock has no strength worth mentioning. Theia came into the Earth like a droplet joining a larger droplet, and the outer layers of both worlds sheared sideways and flung out into space in a long curving arm of molten and vaporized rock. Most of it came back down within hours. The Earth was left completely liquid, glowing, and spinning far faster than before. Its axis was knocked over into a tilt. But some of that arm was moving fast enough and was far enough out that it did not fall back. It kept going, spread into a ring, and began to orbit. That ring is the moon before it was the moon. How long it stayed a ring is a matter of real disagreement. The older models suggested that material in orbit clumps fast and that a recognizable moon existed within something like 100 years, a century from ring to world. Newer work argues for a slower, messier process. Either way, the answer is measured in decades or centuries, not in millions of years. On the scale of everything else in this documentary, the moon appeared instantly. It formed close, very close. We will come back to exactly how close in the next section because it deserves its own space. Now, how do we know any of this happened? We should be honest that the giant impact idea is a reconstruction. Nobody watched it. There is no piece of Theia sitting in a museum with a label on it. What we have is a set of clues and a hypothesis that explains it better than the alternatives, and a long argument about whether it explains them well enough. Before the Apollo program, there were 3 serious theories about where the moon came from, and all 3 of them are now dead. The first was fission. In 1898, George Darwin, the son of Charles Darwin and a serious mathematician in his own right, proposed that the early Earth spun so fast that it threw off a piece of itself. For a long time, people liked the idea that the missing piece was the Pacific Ocean basin. It is a lovely image. It is also wrong on several counts. The Earth would have had to spin roughly twice as fast as anything the physics allows, and the Pacific Basin is not remotely old enough. The second was capture.
The moon formed somewhere else in the solar system and wandered close enough to be caught by Earth's gravity. The problem is that capture is very hard. An object approaching a planet gains speed as it falls in, and unless something removes that energy at exactly the right moment, it swings past and leaves. Capture happens, but it happens to small objects, not something a quarter of your own width. The third was coaquitation. The Earth and the Moon formed side by side out of the same part of the disk, like a double planet. This was the most respectable theory, and it had the fewest obvious problems. It also cannot explain the single most important number about the Moon. The Moon has almost no iron core. The Earth's core is roughly a third of its mass. The Moon's is around 2%. If two worlds formed side by side out of the same material, they would have similar proportions of iron. They do not. The Moon is made almost entirely of the kind of rock that sits in a planet's outer layers, and it's missing the heavy metal that should have sunk to its middle. That's exactly what you'd expect if the Moon were made from the outer layers of two planets after the iron in both had already sunk out of reach. In 1975, two papers proposed the impact independently. One was by William Hartman and Donald Davis. The other was by Alastair Cameron and William Ward. For several years, almost nobody paid attention. Then, at a conference in Kona, Hawaii in 1984, the community effectively agreed that the giant impact was the best answer available, and it has been the standard model ever since. Which brings us to the rocks and to the problem. Oxygen is the most common element in rock, and it comes in three stable varieties, called isotopes. They behave identically in chemistry. They differ only in weight, and the exact ratio between them varies depending on where in the solar system a body formed, because the mixing was never perfect and the disk was never uniform. This makes oxygen ratios a kind of fingerprint. Every world has its own. Meteorites from Mars have a Martian oxygen ratio, and it's measurably different from ours. That's how we know they are Martian. Meteorites from Vesta have a Vestan oxygen ratio. The differences are small, but they are consistent, and they are far outside the measurement error. The Apollo samples came back, and the Moon's oxygen ratio was measured, and it matched the Earth's.
Not approximately, not within the general neighborhood. It matched to within a handful of parts per million, which is to say, it matched as well as two rocks from opposite sides of the Earth match each other. Now hold that against the simulations. Every model of a giant impact says the same thing. In a collision like this, the debris that ends up in orbit comes mostly from the object that hit, not from the object that was hit. Somewhere between 60 and 80% of the Moon should be made of Theia, and Theia, being a separate world that formed somewhere else, should have had its own fingerprint. So the Moon should look chemically foreign. It does not. It looks like us. This is called the isotopic crisis, and it very nearly killed the theory in the 1990s and 2000s. It is one of the best examples in planetary science of a model that explains almost everything and then trips over one measurement. There are three ways out, and the field has not fully settled on which is right. The first is that Theia was born in the same neighborhood, from the same material, and simply had the same fingerprint. If Theia grew in a stable point along Earth's own orbit, as we discussed, this follows naturally, elegant and possible, and difficult to prove. The second is that the impact was more violent than the standard model, violent enough to vaporize a large fraction of both worlds and mix them thoroughly before anything condensed. In 2017,
Simon Locke and Sarah Stewart described what such an object would look like. Not a planet with a ring, but a single vast donut of glowing vaporized rock, too hot and too fast spinning to have a surface at all. They named it a synestia. The moon would have condensed inside it out of a fully blended mixture, which would erase any difference between Earth and Theia. The third is that the Earth and Moon exchanged material after the impact while both were still molten and wrapped in a shared atmosphere of rock vapor until their chemistry evened out. All three are live, none is confirmed. This is a genuinely unsettled corner of the subject, and anyone who tells you it is closed is telling you a tidier story than the evidence supports. What almost nobody disputes anymore is the conclusion underneath it. The moon is made of the Earth. It is not a captured stranger, and it is not a twin. It is a piece of this planet's outer layers thrown into the sky by a collision and never allowed to fall back down. There is one more question, and it is the one that is currently moving. When? For decades, the answer was somewhere between 30 and 100 million years after the solar system formed, which puts the impact around 4,510,000,000 years ago. Then the lunar rocks began to argue with that. Many of them appear to have crystallized closer to 4,350,000,000 years ago, which is 160 million years later. In December 2024, a study in the journal Nature offered a way to have both. The argument is that around 4.35 billion years ago, the moon was still close enough to Earth that tidal forces were kneading its interior hard enough to remelt much of it. A remelting resets the clocks. The rocks would then record the remelting, not the birth. So there are two camps. One says the moon is old and the rocks are lying because they were reheated. The other says the rocks mean what they say. The evidence currently leans toward the first, but it leans and it does not settle. It's worth saying what the impact did to us, because the moon is only half of what came out of it. The Earth's rotation was reset. Whatever it had been doing before, afterward it turned once every 5 hours or so, and the moon has been slowing it down ever since. The Earth's tilt was set. Our axis leans about 23.5 degrees out of vertical, and that lean is the entire reason there are seasons. Summer and winter are not caused by distance from the sun. They are caused by which hemisphere happens to be leaning toward it. That lean is almost certainly a souvenir of the collision. And the Earth's chemistry was altered. The impact stripped away whatever early atmosphere the planet had. Theia's iron core sank down and merged with our own, which means the Earth's core is partly made of another world. Whether the impact also delivered or destroyed our water is still argued over, and the answer changes depending on where you think Theia formed. There is a version of this planet where the collision never happened. It would have no large moon, weaker tides, a day still measured in hours rather than a day, an unstable tilt, and a smaller core. Whether anything would be alive on it is a question no one can answer. Because whichever date is right, the next part is the same. Whatever formed out of that ring came out of it as a ball of liquid rock hundreds of miles deep, with no surface at all.
Look up tonight, and the first thing you will notice, before any crater or any dark patch, is that the moon is white. That whiteness has a cause, and the cause is that the moon was once entirely liquid. When the debris ring pulled itself together, everything that went into it was already hot. The impact had vaporized rock. Condensing rock vapor released enormous heat, and then all of that material fell together under its own gravity, which released more heat still. There was no way for a body forming that way to be anything other than molten. So the newborn moon had an ocean on it, not of water, of liquid rock, somewhere between 200 and 600 miles deep, and possibly all the way to the center. Its surface temperature would have been well over 2,000 degrees Fahrenheit. It glowed. From the Earth, which was also glowing, it would have been a large, dull red disk, visible in daylight, giving off its own light at night. This is called the lunar magma ocean, and the idea did not come from a model. It came from a rock. When the first Apollo samples were opened in 1969, the geologists found something they were not expecting. Mixed into the dark soil of the Sea of Tranquility were small, bright white fragments, chips of a rock called anorthosite. And Tranquility is nowhere near the bright highlands. Those chips had been thrown there by distant impacts from hundreds of miles away. Within months, a group of scientists proposed that the entire bright surface of the moon was made of this material, and that the only way to make so much of it was to melt the whole world and let it separate. Here is the mechanism, and it is worth going slowly because it explains what you can see with your own eyes from your own window. When a body of molten rock cools, it does not freeze all at once. Different minerals crystallize at different temperatures, and once they crystallize, they either sink or float, depending on their density. The first minerals to form in the lunar magma ocean were olivine and pyroxene. Both are rich in iron and magnesium. Both are dense. They sank, and they built the moon's mantle from the bottom up. As they sank, they took iron and magnesium out of the remaining liquid, which changed what the liquid was made of, which changed what crystallized next. Eventually, the melt became rich enough in calcium and aluminum for plagioclase feldspar to start forming, and plagioclase is light. It is less dense than the liquid it grows in. So it floated. Over tens of millions of years, plagioclase crystals rose through hundreds of miles of magma and collected at the top, packing together into a global crust of nearly pure white rock, a layer of frozen foam 20 to 30 miles thick, floating on a still molten world. That crust is what you were looking at when you look at the pale parts of the moon. Not most of the moon, all of the original moon. Everything else came later and only covered a fraction of it. The dark patches you can see are younger and thinner and cover less than a fifth of the surface. We'll get to them. But the white is the moon's original skin, and it has been there, essentially unchanged in composition, for 4.33 billion years. It's worth picturing what that terrain actually looks like, because the word highlands is misleading. It does not mean mountains in the sense of the Alps or the Rockies. There are no ranges built by colliding plates, because there are no plates. The lunar highlands are rolling, soft-shouldered hills, one running into the next, the whole landscape rounded off by 4 billion years of overlapping impacts. Apollo 17 landed in the middle of it, and the photographs look less like a mountain range than a chalk downland that has been shelled continuously since the beginning of time. The genuine mountains on the moon are all crater rims and basin walls. The Apennines, which rise up to 3 miles above the plain, are the uplifted edge of an impact. Every named lunar range is the same. They are not built up, they are what was left standing. There is a rock that proves this, and it has a name, and the name is a little too dramatic for what it is, but the rock itself is genuinely one of the most important objects any human being has ever picked up. On the 26th of July 1971, Apollo 15 launched with David Scott and James Irwin. They landed near Hadley Rill at the foot of the Apennine Mountains, which are not really mountains in the way Earth has mountains. They are the uplifted rim of an impact. On their second surface excursion, they stopped at a small crater called Spur. Scott brushed the dust off a rock sitting on a low pedestal of soil, and both men recognized immediately what they were seeing. You can hear it on the recording. It is white and it is crystalline, and it is exactly what the geologists had told them to look for. It was cataloged as sample 151415. The press called it the Genesis Rock, on the assumption that it dated from the birth of the moon. It doesn't quite. Careful dating puts it at around 4,100,000,000 years, which makes it a piece of the original crust that was later disturbed and reset by an impact. But it is Pharaohan anorthosite. It is a fragment of the flotation crust. It is a physical piece of the frozen surface of a molten world, and we went and got a piece of it. There is one more thing the magma ocean left behind, and it is invisible, and it explains almost everything strange about the moon's later life. Think about what is left at the end of that crystallization process. The dense minerals sank, the light minerals floated. But some elements do not fit comfortably into the crystal structure of either. They're the wrong size or the wrong charge. So they stay in the liquid, getting more and more concentrated as the liquid shrinks. By the end, there was a thin layer of leftover melt trapped between the new crust above and the new mantle below, loaded with everything that had been rejected by both. Geologists call this residue creep. It's an acronym, and it is spoken as word. K is the chemical symbol for potassium. REEY stands for rare earth elements. P is phosphorus. It also carries the moon's uranium and thorium, which are radioactive, and radioactive elements produce heat as they decay. So this leftover layer is not just chemically odd, it's warm. It's the moon's internal heating element. And here's the part that matters. It's not spread evenly. Almost all of the moon's creep is concentrated in one region on the near side, under and around the great dark plain we call the Ocean of Storms. Geologists call the region the Procellarum creep terrain. On the far side, there is very little of it. Nobody's fully explained why. It is one of the two great asymmetries of the moon, and the other is the crust itself, which is roughly 20 miles thick on the side facing us and closer to 35 on the side facing away. Two hemispheres, one thin and warm and chemically loaded, one thick and cold and plain. That difference is the reason the near side has dark seas and the far side almost does not. It is the reason the face you see in the moon exists at all. And we'll spend a whole section on it later because the explanations are genuinely competing, and one of them is wonderful. While we're inside the moon, we should finish the cross-section because the seismometers Apollo left behind eventually told us the whole thing. Beneath the crust is a mantle of dense magnesian and iron-rich rock, which makes up the overwhelming bulk of the moon. Beneath that, at the very center, is a core, a small one. Reanalysis of the Apollo seismic data published in 2011 and independent work using orbital tracking published in 2023 both point to the same structure, a solid inner core about 250 miles across, wrapped in a fluid outer core, wrapped in a partly molten boundary layer where the mantle has never quite finished freezing. That core is about 1% of the moon's volume. The Earth's is 16%. It is the missing iron from Section 2, and it is the strongest single piece of evidence that the moon is made of a planet's outer layers rather than a whole planet. The moon has no magnetic field today. Take a compass there and it will drift aimlessly, but it used to have one. Apollo samples came back magnetized, which can only happen if they cooled in the presence of a field. So for a stretch of its early life, roughly between 4¼ and 3½ billion years ago, and possibly weakly for a good deal longer, the moon had a molten, churning core generating a magnetic field the way the Earth's does now. Then the core cooled too far to keep turning, and the field died. What's left is patchy, frozen magnetism locked into individual rocks, which produces strange local anomalies scattered across the surface. We'll come back to what those anomalies look like from orbit because they are one of the genuinely unexplained things about the moon's appearance. For now, picture the finished object,
A world the size of Australia, wrapped in a white crust it made by floating, still hot underneath, with a thin band of radioactive leftovers hidden beneath one hemisphere. And it was not where it is now, not remotely. It was so close that from the surface of the Earth, if there had been anyone to look, it would not have been a disk you could cover with a fingernail. It would have been a wall.
Tonight, if you hold your arm out straight and raise your thumb, you can cover the moon completely. It takes up about half a degree of sky. It is, in visual terms, a small object. It has not always been small. When the moon formed, it was somewhere between 12,000 and 25,000 miles from the Earth. Today, it averages 238,855 miles. So call it 10 to 20 times closer, and understand what that does to its apparent size. A moon at 15,000 miles would have spanned something like 15 degrees of sky. That is 30 times wider than the moon you know, and 900 times the area. It would not have looked like a light in the sky. It would have looked like a landscape hanging overhead, close enough that you could see its features change as it turned. And it moved fast. At that distance, it would have gone around the Earth in something on the order of 10 hours, so it would rise and set more than twice in a single 5-hour day, crossing the sky visibly in real time, the way a slow aircraft does. Neither of those things is true anymore, and the reason is the reason for this entire documentary. The moon pulls on the Earth, not evenly. The side of the Earth facing the moon is closer to it than the center of the Earth, and the far side is further away, and gravity weakens with distance. So the near side is pulled harder than the middle, and the middle is pulled harder than the far side. The result is that the Earth gets stretched very slightly along the line pointing at the moon. That stretch raises two bulges, one under the moon and one on the opposite side. This is the tide, and it is not only the ocean. The solid rock of the Earth rises and falls by about a foot twice a day, everywhere, including under your house. You have never felt it because everything around you rises and falls with you. Now, the crucial part. The Earth spins once every 24 hours. The moon takes 27 1/3 days to go around the Earth. So the Earth turns underneath its own tidal bulges, dragging them forward faster than the moon can keep up with them. Friction between the water and the seabed means the bulge is not exactly under the moon. It runs slightly ahead of it. And that leading bulge has mass. It pulls on the moon. Because it sits ahead of the moon, it pulls the moon forward along its orbit, adding energy to it. An object given extra orbital energy does not speed up, it climbs. It moves into a wider, slower orbit, and it drifts further away. At the same time, and by the same mechanism, the moon is pulling backward on that bulge, dragging against the Earth's rotation, slowing it down. So the arrangement has been running for 4.5 billion years. The Earth's spin has been feeding the moon's orbit. Every day is a fraction of an instant longer than the day before, and the moon is a fraction of an inch further away. The ocean is paying for the distance. That was the line in the opening, and this is the machinery underneath it. Which raises an obvious question. How do we know the rate? 1.5 inches a year is an absurd thing to claim to measure. We measure it with mirrors, and we have been measuring it since 1969. On the 21st of July, 1969, before they left, Neil Armstrong and Buzz Aldrin set out a panel about the size of a briefcase covered with 100 small glass corner cubes. A corner cube has a useful property. Light that enters it comes back out in exactly the direction it arrived from, no matter what angle it hit at. You do not have to aim it, you only have to put it down. Apollo 14 left another. Apollo 15 left the largest with 300 cubes. 2 Soviet rovers, Lunokhod 1 and Lunokhod 2, carried French-built reflectors and left them on the surface as well. They have no power, they have no moving parts, they cannot break, and so they have simply continued working for more than 50 years, longer than any other experiment ever placed on another world. Observatories on Earth fire a pulse of laser light at those panels and wait. The round trip takes about 2.5 seconds. Almost all of the light is lost. The beam spreads on the way out until it's a couple of miles wide at the moon, and spreads again on the way back. So a typical shot returns a single photon, and sometimes none. Fire enough shots and the timing becomes extraordinarily precise. We know the distance to the moon to within about an inch. Some stations do better than that. 50 years of that data gives the number in the opening, 1.5 inches a year, 3.8 centimeters if you prefer. Now here's where it becomes interesting, and where a lot of documentaries stop early and get it wrong. Take 1.5 inches a year and run it backwards. 4.5 billion years at that rate puts the moon touching the Earth about 1.5 billion years ago. That's obviously false. We have rocks far older than that. We have fossils far older than that. The moon was not sitting on the Earth's surface during the Precambrian, so the rate must have changed. And it has, dramatically, because tidal friction depends on the shape of the oceans. Tides are efficient at draining the Earth's rotation when ocean basins happen to resonate with them. A basin of the right width and depth sloshes hard. A basin of the wrong shape barely responds, and the continents move. Over billions of years, the oceans have been reorganized many times, and each arrangement has its own tidal efficiency. For long stretches of Earth's history, the moon was retreating far more slowly than it is now. The present rate appears to be unusually high because the current Atlantic happens to be close to resonance. We are living through a fast phase. That is a real and slightly unnerving fact, and it is the honest answer to the arithmetic. We can check it too, which is the part I find most satisfying. Some sedimentary rocks preserve tidal cycles directly. In shallow tidal flats, each tide leaves a layer, and the thickness of those layers varies with the tidal cycle over a month. Count the layers and you can read the number of days in a month hundreds of millions of years ago. These are called tidal rhythmites. Corals do something similar. Many species lay down the fine growth band each day and a coarser pattern each year, so a fossil coral is a record of how many days a year contained. Devonian corals, around 400 million years old, record roughly 400 days in a year. The year has not changed. The day was shorter, about 22 hours. That is a direct physical measurement of the Earth slowing down, taken from an animal that died before there were trees. The same process did something to the moon, and it did it much faster because the moon is smaller and the Earth's pull on it is far stronger than its pull on us. The moon started out spinning at its own rate. The Earth raised tidal bulges in its rock exactly as the moon raises them in our oceans, and those bulges dragged on its rotation until the spin slowed to match the orbit exactly. Once that happened, the same face was locked toward us permanently. Astronomers call it tidal locking or synchronous rotation, and it is not rare. Almost every large moon in the solar system is locked to its planet. It happened early, probably within the first few tens of millions of years, which means that essentially the entire history of the moon, one hemisphere has faced us and one has faced away. No creature that has ever lived on this planet has seen the other side with its own eyes from the ground. Not one in 4 billion years of life on Earth. There is one more consequence, and I promised it at the start, so here it is. The Earth's axis leans about 23.5 degrees, and that lean is what gives us seasons. For a planet on its own, that angle is not stable. Gravitational nudges from the other planets, particularly Jupiter, can make an axis wander over millions of years. Mars is the example. Its tilt has swung between roughly 13 and 45 degrees, which has moved its ice caps around and rewritten its climate repeatedly. In 1993, Jacques Lescar and colleagues published calculations suggesting that without a moon, the Earth's tilt would still wander chaotically, possibly across tens of degrees. A planet whose poles sometimes point at the sun does not have a stable climate in any sense a living thing would recognize. That result got repeated everywhere, usually in the form of a flat claim that the moon made life on Earth possible. It has since been challenged. Later work, including a study by Jack Lesauer and colleagues in 2011, found a moonless Earth's tilt would still vary, but far less dramatically than the original figures implied, and perhaps not catastrophically at all. So, the honest version is this. The moon steadies our axis. It probably makes the climate more predictable over very long periods. Whether that was necessary for life or merely convenient is not settled, and anyone stating it confidently in either direction is going beyond the evidence. One small everyday consequence before we move on. The day is getting longer by roughly 1.7 milliseconds per century. That sounds like nothing, and over a human life, it is nothing. But atomic clocks do not care what sounds like nothing. They keep perfect time while the planet does not, and a gap has to be closed by hand. That's what a leap second is. Since 1972, extra seconds have been inserted into the world's official timekeeping to keep atomic time aligned with the actual rotation of the Earth. Every one of those inserted seconds is, in part, a bill from the moon. That's the arrangement we inherited. A close, fast, glowing moon slowly retreating and slowly locking, while the Earth cooled around it. And while all of that was settling, the solar system was still full of debris that had not yet found a home. The sky was not empty. Things were still falling. They fell for a very long time, and the marks are still there because on the moon, nothing ever heals.
Every crater on the moon is a hole where something used to be moving. There is no weather there. No rain, no rivers, no wind, no plate tectonics. Nothing to fill a hole in or wear a rim down, except more impacts and a slow rain of dust. So the moon has kept its record. It is the closest thing the inner solar system has to a written history. And Earth's own history for this period has to be read off it, because our version was destroyed long ago. For the first several hundred million years after the moon formed, material was still falling. Not constantly and not in everywhere at once, but often enough and hard enough that the largest of those impacts did not make craters. They made basins. The distinction matters. A crater is a hole. A basin is a structural event. Above a certain size, the ground beneath the impact behaves like a liquid. It rebounds. It collapses inward in concentric rings, like the rings that spread when you drop a stone in still water, except frozen in rock and hundreds of miles across. The most beautiful example is Mare Orientale, on the western limb, right at the edge of what we can see from Earth. From the ground, it is almost impossible to make out because we see it nearly edge on. From orbit, it is a perfect bullseye, 3 rings deep, about 600 miles across. It is the youngest of the Great Basins, around 3.8 billion years old, and it is the least modified, which makes it the textbook example of what all the others looked like when they were fresh. But Orientale is not the biggest, not remotely. On the far side of the Moon, stretching from near the South Pole up across almost a quarter of the entire globe, there is a depression about 1,600 miles across and in places more than 5 miles deep. It is called the South Pole Aitken Basin. It is the oldest and largest impact structure on the Moon, and it is the largest confirmed impact structure anywhere in the solar system. You cannot see it from Earth, not any part of it. It is a scar big enough to swallow the distance from Los Angeles to Chicago, and no human being had any idea it existed until spacecraft went around the back and measured the shape of the ground. The impact that made it was violent enough to punch through the crust entirely and possibly into the mantle beneath, which is why it has been the single most wanted destination in lunar science for decades. If you want to know what the inside of the Moon is made of, you do not have to drill. You only have to go and pick up what the impact already excavated. In June 2024, that finally happened. A robotic mission called Chang'e 6, run by the China National Space Administration, landed inside the Apollo crater within the South Pole Aitken Basin, collected material, and launched it back to Earth. 1,935 grams, about 4¼ pounds. It is the first material any human effort has ever returned from the far side of the Moon. Everything we had before this, all of Apollo and all of the Soviet lunar landers, came from the near side. The results have been arriving ever since, and they have been substantial. The basin itself now has a measured age, around 4,250,000,000 years, which puts it within roughly 300 million years of the Moon's formation. It is very nearly as old as the Moon's surface can be. And in February 2026, a study in the Proceedings of the National Academy of Sciences, led by Hengqi Tian at the Institute of Geology and Geophysics in Beijing, reported something stranger. The potassium in those far-side basalts is isotopically heavier than the potassium in every Apollo sample ever measured. Not by much, around 0.16 parts per thousand, but it is consistent, and it's well outside the era. The heavier potassium is a fingerprint of vaporization. When rock is heated hard enough to boil, the lighter isotopes escape preferentially, and the heavier ones stay behind. So the reading suggests that the South Pole Aitken impact did not just dig a hole, it stripped volatile elements out of an enormous volume of the Moon's interior, and it dumped in enough heat to start the mantle beneath it convecting. The conclusion the authors draw is that this single impact reorganized the inside of one hemisphere of the Moon, and that the effects lasted billions of years. That is a large claim. It's one study. It's recent, and it will be tested. But it is the current state of the argument, and it is the strongest evidence yet that the Moon's two faces were set apart very early by a single event. Now, the part of this section that is genuinely unsettled and where I want to be careful with you. When the Apollo samples were dated in the early 1970s, a pattern appeared that nobody expected. An unusual number of them recorded the same rough age, around 3.9 billion years.
In 1974, Fuad Teda, Dmitry Papanastasio, and Gerald Wasserberg at Caltech proposed an explanation. They suggested there had been a spike, a relatively brief, extremely violent episode several 100 million years after the solar system settled down, in which the inner planets were pounded far harder before or since. They called it the lunar cataclysm. It is more commonly known now as the late heavy bombardment.
For 30 years, it was close to standard. It was given a mechanism too. In the mid-2000s, a model called the NICE model proposed that Jupiter and Saturn drifted into a resonance, destabilized the outer solar system, and flung a wave of debris inward. It is a compelling story. It may not be true. The core problem is sampling. Every Apollo landing site is on the near side, and most of them are within reach of the debris thrown out by one enormous impact, the Imbrium basin. If a large fraction of the samples are actually Imbrium ejecta, then they all record the same date because they all record the same single event, not a solar system-wide storm. The alternative view is that the bombardment simply declined smoothly from the beginning, tailing off over hundreds of millions of years with no spike at all. There are two camps, and they are both serious. The evidence has been drifting away from a sharp cataclysm for about 20 years now, and toward a long, declining tail with some large events scattered through it. But it is not settled, and the far side samples are exactly the data that might settle it. Nobody knows yet. That is the honest position. What is not in doubt is the roll call of what hit and when. Nectaris on the near side around 3.92 billion years ago. Serenitatis, which forms one of the eyes of the face people see in the moon. Crisium, a near-perfect oval you can pick out with binoculars on the eastern edge. And Imbrium, around 3.9 billion years old and some 750 miles across, which is the single most important scar on the visible moon. Its ejecta blanket covers much of the near side. Its rim is the Apennine Range that Apollo 15 landed against. Almost every sample we have is contaminated by it in one way or another. Then Orientale, about 3.8 billion years ago, and after that, the Great Basins stopped. The solar system had swept itself mostly clean. What remained was the ordinary background rate of impacts, which continues to this day, and which is thousands of times lower. That rate is not zero. LRO has photographed the same terrain repeatedly for over a decade and found hundreds of craters that were not there on the previous pass. Small ones. But the moon is still being hit tonight while you are listening to this. Two more things about craters because they are the moon's dominant feature and most people have never been told how they work. The first is that craters are almost always round, regardless of the angle the impactor came in at. This surprises people because a stone thrown into mud at a low angle makes an oval scar. But at impact speeds, several miles per second, the incoming object is not really digging, it is delivering energy. The energy expands spherically from the point of contact, and the resulting hole is round almost no matter what. Only impacts below about 15 degrees leave an elongated crater. The second is the central peak. In craters above a certain size, the floor rebounds after the impact, like the drop of liquid that jumps back up in the middle of a splash and then freezes in place. Those peaks are made of material dragged up from deep beneath the surface, which makes them the cheapest possible way to sample a planet's interior. And then there are the rays. Look at the full moon and you'll see bright streaks spreading out from a point in the southern highlands, running for hundreds of miles across everything in their path. That's Tycho crater, 53 miles across and only 108 million years old, which makes it a newborn. Its rays are fresh ejecta, still bright because they haven't yet been darkened by billions of years of space weathering.
Some of them reach more than 900 miles. Copernicus, further north, is 58 miles wide and around 800 million years old, and its rays are noticeably fainter. That fading is itself a clock, which is how the Moon dates the rest of the solar system. Count the craters on a surface. More craters means more time exposed. Because Apollo brought back rocks from known locations with known crater densities, we have a calibrated relationship between crater count and absolute age. That calibration is then applied to Mars, Mercury, and every other airless surface we have imaged. When you read that a Martian lava plain is 3 billion years old, that number ultimately traces back to a box of rocks carried off the Moon by astronauts in the 1970s. So picture the Moon at 3.8 billion years ago. White crust punched through in a dozen places by basins hundreds of miles wide. The largest of them on the far side, deep enough to have reached toward the mantle. All of them empty. Vast circular depressions with terraced walls and central peaks and nothing inside them at all. They did not stay empty. Underneath the crust, that layer of radioactive leftovers had been quietly heating the interior for 600 million years, and the basins had thinned the crust above it. The Moon was about to bleed.
Look at the Moon with nothing but your eyes, and you will see a pattern of dark patches on a pale surface. Human beings have been looking at that pattern for as long as there have been human beings, and every culture has read something into it. In Western Europe, it became a face. In parts of East and South Asia, it is a rabbit. And once you have been shown the rabbit, it is very hard to go back to seeing the face. In some indigenous North American traditions, it is a frog or a toad. The Maori slaw a woman. They are all looking at the same thing. Floods of lava that erupted onto the surface between roughly 3.8 and 3 billion years ago, and then froze in place and have not moved since. The name we use for them comes from a mistake, and it is a very old and rather lovely mistake. When Galileo turned his telescope on the Moon in 1610, he saw smooth, dark regions and rough, bright ones, and he reasonably assumed the smooth, dark ones were water. Astronomers of that era gave them names to match. In 1651, the Jesuit astronomer Giovanni Riccioli published a lunar map, and the names he chose are still the official ones today. Sea of Tranquility, Sea of Serenity, Sea of Crises, Sea of Rains, Ocean of Storms, Marsh of Sleep, Lake of Dreams, Bay of Rainbows. Riccioli had a theory that the Moon influenced weather, so he named the regions after moods and conditions, and the result is that the driest place any human being has ever visited is covered in the names of oceans and marshes and rainbows. Neil Armstrong's first words after landing were that the Eagle had landed at Tranquility Base. He was standing in a lava plain named for a body of water by a priest 319 years earlier who thought it was a sea. Here is what actually happened. Under the crust, that creep layer had been generating heat from radioactive decay for hundreds of millions of years. The heat built up. Rock does not need to be fully molten to move, but eventually pockets of the mantle did melt, producing a dense, dark, iron-rich, runny magma called basalt. Basalt is the most common volcanic rock in the solar system. It is what most of the Earth's ocean floor is made of, and what Hawaii and Iceland are built from. It is not sticky. It flows like syrup rather than piling into a cone.
That magma needed a way up, and the Great Impact Basins had already provided one by blasting away much of the crust above. So the lava rose, and it did not build volcanoes. It flooded. It spread out across the floors of the basins in sheets, layer upon layer, over hundreds of millions of years, until the basins were filled and level. That is what the dark patches are, not seas, not craters, ponds of frozen lava sitting inside the scars of much older impacts. They are darker than the highlands because basalt is rich in iron and titanium, and iron-rich minerals absorb light. In the Sea of Tranquility, the titanium content is unusually high, which is part of why the Apollo 11 samples were darker than expected. Now the number that surprises most people. The Maria cover only 16% of the Moon's total surface. 16%. The Moon is overwhelmingly white highland crust, and the dark seas are a thin, patchy veneer. But they are not spread evenly. On the near side, the side you can see, they cover close to a third. On the far side, they cover something like 1 or 2%. That single fact is why the Moon has a face at all. If the far side were pointing at us, there would be no man in the Moon, no rabbit, no woman, no frog. There would be a bright, uniform, crater-saturated disk with nothing to read into it. Every moon myth in human history depends on which way the Moon happens to be facing. The lava flows were not one event. They ran for a very long time. The oldest mare basalts we have are around 3.9 billion years old. The main phase ran from about 3.8 to 3.1, and it kept going weekly for a great deal longer than anyone expected. Here is how we learned that, and it is a nice piece of detective work. In December 2020, the Chang'e 5 mission returned samples from a young-looking lava plain on the near side in the northern ocean of storms. The rocks came back dated at 2 billion years. That was a full billion years younger than anything Apollo brought home, and it meant the Moon was volcanically active far more recently than the sample record had suggested. Then Chang'e 6 returned far-side material, and among it was basalt dated at 2,830,000,000. That matters because the far side was supposed to be the dead hemisphere. Thick crust, almost no creep, no obvious heat source. And yet there was still lava reaching the surface there nearly 2 billion years after the Moon formed. The far side is quieter than the near side. It is not and was not dead.
There is a further claim, and this one is genuinely speculative, so I will label it as such. Scattered across the Maria are small, strange features called irregular mare patches. They are only a few miles across. They have very few craters on them, which normally means a young surface, because craters accumulate over time. In 2014, a team led by Sarah Braden argued that some of these patches may be less than 100 million years old, possibly as young as 50 million, on a moon that was supposed to have gone cold billions of years earlier. If that is right, there was still volcanic activity on the moon when dinosaurs were alive on Earth. That is an extraordinary claim, and it depends on crater counting, which is a statistical method with real uncertainties on small areas. Other researchers have proposed that the terrain is unusual rather than young. It is not resolved, treated as an open question rather than a fact. One more feature, because you can see it in any decent telescope, and because 2 men once drove a rover to the edge of it. Running across some of the Maria are long, winding channels called sinuous rills. They look like dry riverbeds, and for a while, people wondered if they were. They are not. They are collapsed lava tubes or channels carved by flowing lava, which is a thing lava does on Earth as well, only smaller. The most famous is Hadley Rill. It's about 80 miles long, a mile wide, and 1,000 feet deep. Apollo 15 landed beside it in 1971, and David Scott and James Irwin drove the first lunar rover to its rim and photographed layers of ancient lava flows exposed in the far wall like the strata in a canyon. Those exposed layers are a stack of individual eruptions. You can count them. Each one is a separate flood, separated by however long it took before the next. There is a practical consequence to lava tubes, and it will matter a great deal in the next 50 years. Some of those tubes did not collapse. In 2009, a Japanese orbiter photographed a deep vertical pit in the Marias Hills region, and radar and imaging since then indicate it opens into an intact tube beneath. Estimates suggest lunar lava tubes could be enormous, miles wide, structurally stable in low gravity, and roofed by tens of feet of ramuk. Underground, you are shielded from radiation, from micrometeorites, and from the temperature swing between lunar day and night. Almost every serious proposal for a long-term human presence on the moon involves going into a tube or a pit rather than building on the surface. 3 billion-year-old plumbing waiting to be used as shelter. 2 smaller features, both visible from your back garden with modest equipment, both worth knowing about. The first is wrinkle ridges. Look along the terminator, the line between lunar day and night where shadows are longest, and you'll see low, sinuous ridges running across the dark plains like folds in a bedsheet. They are compression features. As the thick pile of lava cooled and settled into the basin beneath it, the surface buckled. Some run for hundreds of miles. And then there is domes. In a few places, particularly a region called the Marias Hills, there are gentle, rounded swellings a few miles across with tiny pits at their summits. They are the closest thing the moon has to a conventional volcano, and they're barely worth the name. On Earth, a shield volcano rises miles. A lunar dome rises a few hundred feet. And then there is the Aristarchus Plateau, which is the strangest volcanic terrain on the moon. It's a raised block on the near side, covered in the darkest material anywhere on the surface. Those deposits are pyroclastic. They were not lava flows. They were fire fountains, gas-driven eruptions that sprayed molten rock high above the surface, where it froze into tiny glass beads and fell back as a blanket of black sand. The Apollo 17 orange soil came from exactly this kind of eruption. The Aristarchus deposit is the largest of them, covering an area roughly the size of West Virginia. Sitting in the middle of it is Aristarchus crater itself, 25 miles wide and one of the brightest objects on the lunar surface. It's bright enough to be visible to the naked eye against the dark plateau, and bright enough that when it is lit only by Earthshine, observers through history have repeatedly reported it glowing. Those reports are the origin of a long-running curiosity called transient lunar phenomena. Brief flashes, hazes, and color changes reported by astronomers over centuries concentrated around Aristarchus. Some are certainly atmospheric effects in our own sky or errors of observation. A few may be outgassing or fresh impacts, which we now know happen often enough to be caught on camera. It is not evidence of anything hidden. It's a reminder that the moon is not quite as static as it looks, and that people have been paying close attention to it for a long time. So the face is a burn, the seas are stone, and the pattern that every human culture has looked up at and named is the frozen record of where the crust was thin enough to bleed. Which leaves the question this section has been circling. Why only on our side?
This is a photograph of a place that no human being saw for the entire history of our species until 1959. Not a place that was hard to reach, not a place that was poorly mapped, a place that was, in the most complete sense of the word, unknown. Half of the nearest object in the sky permanently turned away for every generation of every civilization that ever looked up and wondered about it. We should start by clearing up a phrase because it is used wrongly almost everywhere and it bothers astronomers more than it probably should. There is no dark side of the moon. The far side gets exactly as much sunlight as the near side. Every part of the moon, apart from a few crater floors we will come to shortly, receives about 2 weeks of daylight, followed by about 2 weeks of night. When you look up at a new moon, when the near side is completely black, the far side is in full sun. It is the far side, it is never the dark side. The album is excellent, but the phrase is wrong. Here is something else that is usually stated wrongly. We do not see exactly half of the moon. We see 59% of it. The reason is a set of small wobbles collectively called librations. The moon's orbit is not a perfect circle, so it speeds up when it is closer to us and slows down when it is further away, while its rotation stays perfectly steady. The two get slightly out of step, and the moon appears to rock side to side over the course of a month, letting us peek a little way around each edge in turn. Its axis is also slightly tilted relative to its orbit, so we see a little over the North Pole and a little under the South Pole at different times. Add it all up, and about 59% of the surface is visible from Earth at some point. 41% never is. There is a consequence to this that is easy to miss. Because the moon keeps one face toward us, an astronaut standing on the near side would see the Earth hanging in the same patch of sky permanently. It would not rise and it would not set. It would sit there, going through its phases over a month, wobbling very slightly with libration and otherwise fixed. And an astronaut on the far side would never see the Earth at all, not once, no matter how long they stayed. If you photograph the moon on the same night each month for a year and lay the images side by side, you can watch it nodding. It is one of the easiest real astronomical measurements an amateur can make, and it is oddly moving to see it happen. On the 7th of October 1959, a small Soviet spacecraft called Luna 3 passed behind the moon and took 29 photographs on film. It then developed the film on board using a self-contained chemical process, scanned the negatives with a light beam, and transmitted the results back to Earth as a slow television signal. The images that arrived were blurry, streaked, and low contrast. About 17 of them were usable. And they were the answer to a question every human being who had ever lived had been unable to ask usefully. And the answer was strange. The far side had almost no dark seas. Nobody predicted that. There was no obvious reason for the two hemispheres of a small world to differ. The Soviet team, having got there first, got to name what they found. That's why the far side carries names like Mare Moscovensis, the Sea of Moscow, and the cratered Tsiolkovsky, after the Russian rocketry theorist. Tsiolkovsky is worth a look. It is one of the very few far side craters with a dark lava floor, and it has a brilliant white central peak sitting in the middle of it. It looks like an eye.
9 years later, on the 24th of December 1968, 3 men became the first human beings to see it directly. Apollo 8 carried Frank Borman, James Lovell, and Bill Anders into lunar orbit. Going around the back of the moon meant losing radio contact with Earth entirely for about 34 minutes at a time. There was nothing anyone on the ground could do during those passes. There was no help available. Lovell described the far side later in fairly plain terms. He said it looked like a sand pile his children had been playing in. Beaten up, pockmarked, no definition, just craters on craters on craters. That description is scientifically accurate. The far side is saturated. It has taken so many impacts that new craters can only form by destroying old ones, and the crater count no longer increases. It is as damaged as a surface can get. So why are the two halves different? There are 3 real explanations on the table, and I want to give you all 3 because this is one of those questions where the honest answer is that we don't know yet. The first explanation is the crust. The near side crust is roughly 20 miles thick. The far side is closer to 35, and in places, more. That is a very large difference for a small body. Magma rising from the interior has to reach the surface to make a mare. On the near side, the ceiling was low, and the great impact basins had already thinned it further. On the far side, the ceiling was high, and most magma never got out.
That explains the seas neatly. It does not explain the crust. The second explanation is the heat, and it is the one I find most beautiful. In 2014, a team including Arpita Roy and Jason Wright at Penn State published an argument along these lines. Remember that the moon formed extremely close to the Earth and became tidally locked very early, and that the Earth at the time was still glowing from the impact. That means one hemisphere of the young moon was permanently facing a red-hot planet filling a huge portion of its sky, radiating heat at it continuously for millions of years, with no night from that source ever. The far side, facing away into empty space, cooled faster. Aluminum and calcium, the ingredients of the anorthosite crust, condense at high temperatures. They would have settled out of the early moon's rock vapor atmosphere preferentially on the cold side, building a thicker crust there, while the hot side stayed thin. If that is right, then the face of the moon was carved by the heat of the newborn Earth. The pattern you see when you look up is, indirectly, a shadow of our own planet's infancy. It's a wonderful idea. It is not confirmed. The third explanation is impact. We covered South Pole Aitken in the last section. It's on the far side. It is 1,600 miles wide. The February 2026 potassium result suggests it drove convection through the interior and stripped volatiles from a huge volume of the moon. If a single impact of that size redistributed heat-producing elements toward the opposite hemisphere, it could concentrate the creep layer on the near side, which in turn would drive near-side volcanism for the next 2 billion years. There's a fourth idea too, and it is the most dramatic and the least supported. In 2011, Martin Utzi and Eric Asfaug proposed that the Earth once had a second, smaller moon sharing an orbit, and that the two eventually met at low speed and merged. A slow collision would not make a crater. It would splat the smaller body onto one hemisphere as a layer of extra crust. The press called it the Big Splat. It's a real published hypothesis in a real journal. It is also a minority view, and you should hold it loosely. 4 ideas: crust thickness, Earth-shine heating, the Great Impact, and a second moon. They are not all mutually exclusive. Several could be partly right. Nobody knows. And that's a sentence worth sitting with because it's being said about the most familiar object in the sky, one that 12 people have walked on, and it's still true in 2026. There's one last thing about the far side, and it's about what it's going to be used for. Because it permanently faces away from Earth, the far side is the only place in the inner solar system that is shielded from human radio noise. Every transmitter on this planet, every phone, every radar, every broadcast is blocked by 2,000 miles of rock. Radio astronomers have wanted to put a telescope there for decades. The very low-frequency radio waves from the early universe, from the period before the first stars switched on, are drowned out on Earth and largely blocked by our own ionosphere. On the lunar far side, they would come through clean. It's the quietest place we can currently reach, and what it offers is a view of the one era of cosmic history we have never been able to see. Getting anything to work there is harder than it sounds, and for a reason that is obvious once stated. Radio waves travel in straight lines. 2,000 miles of rock is not transparent to them. A spacecraft on the far side can talk to Earth at all. The solution is a relay. Park a satellite in a slow loop around the gravitationally balanced point beyond the moon, where it can see both the far side and the Earth at the same time and bounce the signal through it. That's how the first soft landing on the far side was achieved in January 2019, when the Chang'e 4 mission set down in the von Karman crater inside the South Pole 8-pin basin and released a small rover. It ran for years, far past its design life, crawling a few hundred yards at a time and photographing terrain no camera had been close to before. Everything humanity has ever placed on the far side has needed that relay, and everything ever placed there will. If you're still awake and this is the kind of thing you want more of, the full story of that quiet side and what we plan to build there is a film in itself, and it's linked below for whenever you next need 3 hours of the universe explained slowly. The eruptions faded, the interior cooled, the last great lava flows drained away and froze. And then, for the next 2.5 billion years, almost nothing happened at all. For most of its existence, the moon has done nothing. That is not a criticism. It is close to the whole point of it. Between roughly 1 billion years ago and the present day, the surface of the moon has changed less than the surface of the Earth changes in an average afternoon. There is no wind because there is essentially no air. There is no rain, no rivers, no ice sheets, no plants, no burrowing animals, and no earthquakes of the kind that fold mountains, and no plate tectonics of any sort. The moon has never had a single plate tectonic plate. Its crust is one continuous shell, and it always has been. So, the record stays. This is why the moon matters scientifically, far beyond its own story. It is a filing cabinet for the history of the inner solar system, and everything that has been filed in it is still there. Which is not the same as saying nothing happens. 3 things happen, slowly, and they are worth going through one at a time. The first is dust. The moon is covered everywhere in a layer of fine gray powder called regolith. It is around 10 to 15 feet deep on the Maria and can be 60 feet or more on the ancient highlands, simply because the highlands have had longer to accumulate it. It is not soil. Soil on Earth is largely the product of life and water. Lunar regolith is pulverized rock made by 4 billion years of impacts, breaking the surface down grain by grain, mixed with tiny beads of glass formed when impacts melted rock and it froze in flight. And because there is no water and no wind to round off the grains, every particle keeps its edges. Lunar dust is sharp, angular, statically charged, and it clings to everything. The Apollo crews hated it. It stuck to the suits and could not be brushed off properly. It came into the lander with them and floated in the cabin. It got into seals and wore them down.
Harrison Schmitt on Apollo 17 developed what he called lunar hay fever from breathing it. Gene Cernan on the same mission said flatly that dust was the #1 problem in returning to the moon. It is still the #1 problem. Every plan for a long-term base has to solve it. Which brings us to a thing people say about the moon that is almost right and worth correcting gently. The Apollo footprints are not permanent. They are extraordinarily durable, and there is nothing to blow them away or wash them out, but the same process that made the dust is still running. Micrometeorites, most of them smaller than a grain of sand, arrive constantly and churn the top layer over. Geologists call it gardening. The rate is slow. Estimates suggest the top inch of regolith is turned over on a timescale of roughly 10 million years. So the footprints will soften, then blur, then vanish over a period measured in millions of years rather than forever. Millions of years is an extraordinary thing. Those prints will outlast the Rocky Mountains in their current form. They will outlast our species almost certainly, but they will go. The second thing that happens is that the moon shakes. Between 1969 and 1977, Apollo crews installed seismometers at 5 landing sites as part of a package of instruments called ALSEP. They ran continuously and sent data back to Earth for years after the last crew left. They recorded around 13,000 moonquakes. There are 4 kinds, and each one tells you something different. Deep moonquakes happen around 430 miles down, and they come on a monthly schedule, which is the giveaway. They are triggered by tidal stress, as the Earth's pull flexes the moon's interior over the course of its orbit. The same process that is pushing the moon away is squeezing it as it goes. Thermal quakes happen at dawn, when the surface has been at minus 280 degrees Fahrenheit for 2 weeks and sunlight suddenly begins to warm it. Rock expands. Rock cracks. The moon ticks as it heats, like a car engine cooling in a driveway, only enormously larger and in reverse. Impact quakes are exactly what they sound like. Something arrives. And then there are shallow moonquakes, which are the interesting ones and the concerning ones. They occur in the upper crust, and they are far stronger than the rest, and the largest recorded reached around magnitude 5.5. On Earth, that's enough to crack plaster and knock things off shelves. What makes them alarming for anyone planning to build there is not the strength, it is the duration. On Earth, a quake fades within a minute or 2 because rock full of water and fractured by weathering absorbs vibration efficiently. The moon is bone dry and fractured all the way down. So it does not absorb, it rings. The first time anyone realized this was in November 1969, when the Apollo 12 crew deliberately crashed their lunar module's ascent stage into the surface after returning to orbit. The seismometer they had left behind picked up the impact and kept picking it up. The vibrations continued for around an hour. The moon rang like a bell. That phrase has been badly misused since then by people who want it to mean the moon is hollow. It is not hollow, and the seismic data is in fact how we know its internal structure in detail, including that it has a small iron core. It rings because it is dry and cracked. That's all, and it is interesting enough on its own. There is a coda to this. In 2024, Keisuke Onodera at the University of Tokyo reprocessed the original Apollo loon tapes with modern noise reduction and found roughly 22,000 additional events that had been sitting in the archive unnoticed for 50 years. That would take the total to about 35,000.
That work was presented at a conference and was in review at the time of writing, so treat the higher figure as promising rather than established. But the original 13,000 is solid, and it came from instruments switched off before most people listening to this were born. The third thing that happens is that the moon is shrinking. As the interior has cooled over billions of years, it has contracted. The crust, being a single, unbroken shell with nowhere to go, has had to wrinkle to accommodate it. The result is a feature called a lobate scarp. They look like long, low, curving cliffs, often only tens of feet high but running for miles. They are thrust faults. One block of crust has been pushed up over another. The Lunar Reconnaissance Orbiter has now mapped thousands of them, and the key observation is that they look fresh. They cut across small craters rather than being cut by them, which means they formed recently in geological terms. Some of them may be less than 50 million years old, and some may still be active. The estimate is that the moon's radius has shrunk by around 150 feet over the last several hundred million years. That is not a large number for an object 2,159 miles across, but it is not zero, and it means the moon is not a dead world in the strictest sense. It is a cooling one, still adjusting, still cracking. Some of those scarps are near the South Pole in the region where crews are meant to land. That is a live engineering concern, not a hypothetical one. So, the conditions. Let me lay them out plainly, because this is the world the Apollo crews walked into, and it is the world Artemis crews will walk into. At the equator, the surface reaches about 250 degrees Fahrenheit in daylight and falls to about -280 at night. A single day and night cycle takes about 29.5 Earth days, so each is roughly 2 weeks long. There is technically an atmosphere. It is called an exosphere, and it is so thin that its molecules essentially never collide with one another. There are around 100 molecules per cubic centimeter. On Earth, at sea level, there are about 10 billion. The moon's entire atmosphere gathered together would weigh a few tons. The sky is black in daylight because there is no air to scatter sunlight into blue. The stars are up there the whole time, but the surface is so brilliantly lit that human eyes adapted to it cannot see them, which is why Apollo photographs show black skies with no stars in them. And it is silent. Not quiet, silent. Sound needs a medium, and there is none. The astronauts could hear their own suits and their own radios and nothing else ever. Two last things, and they are both about the moon looking stranger than a dead world ought to. Scattered across the surface are features called lunar swirls. They are bright, sinuous, looping markings, some tens of miles across, that look painted on. They have no topography whatsoever. Run a laser altimeter over one and the ground is flat. They are purely a difference in brightness. The best known is Reiner Gamma in the Ocean of Storms, which through a telescope looks like a smudge someone left with a thumb. And they sit on top of the magnetic anomalies we mentioned earlier, the patches of frozen magnetism left over from the moon's dead core. The leading explanation is that those little magnetic fields deflect the solar wind. Space weathering, the slow darkening of exposed lunar rock, is driven partly by the constant stream of charged particles from the sun. Where a magnetic patch shields the ground, the surface stays pale. The soils are, on this reading, sunburn shadows, places that have been standing under a parasol for 1 billion years. It's a good explanation, it is not confirmed, and there are competing ideas involving dust sorting by electric fields. Nobody has been to one. A small NASA mission to fly close to Reiner Gamma has been in development for exactly this reason. The other thing is that the moon has a tail. Sodium atoms are knocked off the surface by micrometeorite impacts and by sunlight itself, and once free, they are pushed away from the sun by the pression of light. The result is a faint stream of sodium extending hundreds of thousands of miles behind the moon, like a comet's tail. Far too dim for the eye, but detectable with the right instrument. When the moon is new, that tail points at the Earth, and our gravity focuses it into a narrow beam that continues past us. For a few days each month, there is a thin spot of lunar sodium glowing in our own night sky, and nobody looking up has any idea it is there.
3 billion years of this, dust settling 1 grain at a time, the ground ticking at dawn, the occasional deep tremor as the Earth pulled at it, a cliff wrinkling upward over a plain over 10 million years. No witness to any of it. And then, in a period of 3.5 years, 12 people arrived. 12 people have stood on the surface of the moon. All of them were American. All of them were men. And all of them did it inside a period of 3 years and 5 months. Nobody has been back since. The last person to leave was Eugene Cernan on the 14th of December, 1972. And as I record this, more than 53 years have passed. This section is not about the politics of why that happened, and it is not about the launches, which have been told well elsewhere. It is about what they brought back. Because everything you have heard tonight, every date and every mechanism exists because of 842 pounds of rock. It begins before the landings. Apollo 8, December 1968, went to lunar orbit and came home. The crew read from the Book of Genesis on Christmas Eve to what was then the largest television audience in history. And on the 4th orbit, William Anders looked up, saw the Earth coming over the lunar horizon, and asked for a roll of color film in a hurry. The resulting photograph is usually called Earthrise. It is often credited with helping start the modern environmental movement, which may be too neat a story, but the image did something measurable to how people thought about the planet. The first Earth Day followed 16 months later. They also became the first human beings to leave Earth's gravitational dominance and the first to see the far side directly. Apollo 11, the 20th of July, 1969. Neil Armstrong and Buzz Aldrin landed in the Sea of Tranquility, with famously very little fuel left, having flown manually past a boulder field that the automated system was steering them into. They were on the surface for 21 hours and 36 minutes, and outside for about 2.5. They collected 47.5 pounds of samples, deployed the laser retroreflector we discussed earlier, and left. It was scientifically a modest mission. It was never meant to be otherwise. The point was to prove it could be done and to get everyone home. The science came afterward, and it escalated fast. Apollo 12, November 1969. Charles Conrad and Alan Bean made a pinpoint landing about 600 feet from Surveyor 3, an uncrewed probe that had been sitting on the moon for 2.5 years. They walked over, photographed it, and cut pieces off it to bring home, so engineers could see what 2.5 years of lunar exposure does to hardware. That is the first time any human being has ever visited a spacecraft on another world. Apollo 13, April 1970, did not land. An oxygen tank ruptured 2 days out. The crew used the lunar module as a lifeboat, swung around the far side of the moon on a free return trajectory, and came home. In doing so, James Lovell, Fred Hayes, and John Swigert traveled farther from Earth than any human beings before or since, because the moon happened to be near the far end of its orbit. That record stood for 56 years. Apollo 14, February 1971, went to Fra Mauro, the site Apollo 13 had been aiming for. Alan Shepard, who had been the first American in space a decade earlier, and Edgar Mitchell hauled a wheeled cart around the rim of Cone Crater and, famously, could not find it, having walked past the edge without recognizing it in the featureless terrain. Shepard hit 2 golf balls before leaving. Apollo 15, July 1971, is where the program became genuinely scientific. David Scott and Edgar Irwin brought the first rover, which extended their range from a few hundred yards to miles. They landed beside Hadley Rill in the Apennine Mountains,
and found sample 15415, the anorthosite from Section 3. Scott also performed the demonstration everyone remembers, dropping a geological hammer and a falcon feather together in front of the television camera and watching them land at the same instant because there is no air to slow the feather. Galileo's prediction tested on the moon 350 years later. Apollo 16, April 1972. John Young and Charles Duke landed in the Descartes Highlands, chosen because geologists expected to find volcanic rocks there. They found impact breccias instead, which meant a widely held idea about lunar highland volcanism was simply wrong. That is a mission succeeding by disproving the reason it was sent. Duke left a photograph of his family on the surface, wrapped in plastic. It is still there. The plastic has almost certainly failed, and the image has almost certainly faded to nothing in the ultraviolet, but the object remains. Apollo 17, December 1972. The last one, and the best one. Eugene Cernan flew with Harrison Schmitt, who was a professional geologist, the only scientist ever to walk on the moon, and who was added to the crew after the cancellation of later missions made it clear there would be no other chance. They landed in the Taurus-Latreille Valley, a deep valley between mountain blocks. On their second excursion, at a small crater called Shorty, Schmitt stopped mid-sentence. The soil was orange. Orange on a world where everything is gray. He thought it might be evidence of recent volcanic activity, possibly even a fumarole. It turned out to be older, not younger. The orange material is tiny beads of volcanic glass, around 3.64 billion years old, thrown out in a fire fountain.
Eruption when the moon was still hot. The glass is rich in titanium, and it froze in flight before it could crystallize. Those beads also turned out to contain water, locked inside the glass. That discovery came much later, in 2008, using instruments that did not exist when the samples were collected. It overturned the assumption that the moon's interior was bone dry, and it is one of the best arguments for keeping material in storage. Which is the real point of this section. 842 pounds of rock, soil, and core samples came back, around 2,200 separate specimens, which have been subdivided into well over 100,000 cataloged pieces. They live in a nitrogen-filled vault at the Johnson Space Center in Houston, with a second set stored separately in San Antonio in case of disaster. And a fraction of them were never opened. The Apollo teams understood something that is easy to say and hard to actually do. They knew that instruments in the future would be better than instruments in 1972. So they sealed some samples on the lunar surface in vacuum and instructed that they should not be touched. In 2019, NASA began opening them under a program called ANGESA. One of the Apollo 17 core samples, driven into the soil by Cernan and Schmitt and sealed there, was opened in 2022. The scientists who opened it were not born when it was closed. Some of their instruments did not exist as concepts, and the gas that came out of that tube had been sitting inside it undisturbed since before the Vietnam War ended. That is the payoff of the Apollo program, and it is still being collected. A decision made by geologists in 1972 is producing new results in the 2020s, and there is material still sealed for whoever comes after us. They left other things running. The ALESP instrument packages, powered by small nuclear generators, kept transmitting seismic, magnetic, and heat flow data long after the crews were home. They were still working and still returning useful science
when the program to operate them was shut down for budget reasons on the 30th of September 1977. Nobody turned them off because they had failed. They were switched off because there was no money to listen. There are also 6 flags, 3 rovers, a fair amount of discarded equipment, and around 96 bags of human waste, which are of genuine scientific interest to microbiologists wondering whether anything in them survived. And there is a small aluminum sculpture, 3.5 inches long, left by David Scott, next to a plaque listing 14 astronauts and cosmonauts who had died. He placed it and did not mention it publicly until after the mission. It is the only piece of art on another world. The 53 years since are usually described as a gap, and that is not quite fair, because the moon was never actually abandoned. It was only abandoned by people. Robotic missions kept going. The Luna program returned 3 small samples automatically in the 1970s and drove 2 rovers across the surface. Clementine and Lunar Prospector mapped the whole thing in the 1990s. The Lunar Reconnaissance Orbiter arrived in 2009 and has been photographing the surface at high resolution ever since, including images of every Apollo landing site, in which you can see the descent stages, the instrument packages, the rovers parked where they were left, and the tracks. That is worth a moment on its own. You can look at a photograph taken from orbit in the last few years of the paths 2 men walked in 1972, still there, still sharp. And in the last few years, the landings resumed, uncrewed and commercial. In February 2024, a lander built by Intuitive Machines in Houston became the first American vehicle to touch down on the moon since Apollo 17. It caught a foot on landing and tipped on its side, and it worked anyway. In March 2025, Firefly Aerospace landed the Blue Ghost spacecraft upright in the Sea of Crises and operated it through a full lunar day, and it photographed a sunset from the surface. These are cheap missions by the standards of Apollo. They fail often, but they are flying regularly now, carrying NASA instruments as paying cargo, and they are the reason there is any infrastructure at all for what comes next. Cernan climbed the ladder last. He said a few words about coming back in peace with hope for all mankind, and then they lifted off, and the camera on the rover tilted up to follow them because a controller in Houston had timed the movement in advance. Then the valley was empty again, and the dust that had been kicked up settled back down for the last time. 53 years of nothing followed.
At the south pole of the moon, there are places where the sun has not risen for 2 billion years. Not places that are dark at night, places that are dark permanently, that have never once been lit since long before there were animals on Earth, and that will stay dark for as long as the moon holds its current orientation. They are the coldest measured locations in the solar system. They are the reason every space agency on this planet is currently pointed at the same few square miles of ground. And they are by a wide margin the most difficult terrain any human being has ever been asked to land on. Here is why they exist, and it comes down to a single number. The Earth is tilted 23.5 degrees on its axis. That tilt is what gives us seasons. It is why the sun climbs high in summer and stays low in winter, and it is why the Arctic gets a midnight sun in June and total darkness in December. The moon is tilted 1.5 degrees, which means the moon has effectively no seasons, and the sun at its poles never climbs more than about 1.5 degrees above the horizon, ever. It circles the horizon rather than rising over it. Now put a crater there, a hole several miles deep with a raised rim.
If the sun never gets higher than 1.5 degrees, and the crater rim stands higher than that from the point of view of the floor, then no sunlight can ever reach the bottom. Not at any time of year, because there are no years in the relevant sense. Not at any point in the lunar day, because the sun simply goes around. These are called permanently shadowed regions. There are thousands of them at both poles, ranging from patches the size of a parking lot to craters more than 12 miles across. The largest and best known is Shackleton, sitting almost exactly on the South Pole. It is around 13 miles wide and 2.5 miles deep. Its floor has been in darkness for an estimated 2 billion years or more. And because they never see the sun, they never warm up. The Lunar Reconnaissance Orbiter carries an instrument called Diviner, which measures surface temperature. Diviner has recorded floor temperatures in polar shadowed craters as low as 26 Kelvin. That is about minus 416 degrees Fahrenheit. Take a moment with that figure because it is easy to skate past. Pluto's surface is warmer. To find anything colder with a solid surface, you would have to travel out past the Kuiper Belt, beyond the last things we have names for. And it is on the moon, 3 days away. A place that cold is not just cold, it's a trap. Any volatile substance that arrives anywhere on the moon, from a comet impact, from the solar wind, from a passing meteorite, gets warmed by sunlight and bounces. Molecules hop across the surface in long ballistic arcs, going wherever chance takes them. If one of those hops ends inside a permanently shadowed region, the molecule stops. There is not enough heat to give it another jump. It freezes to the ground and it stays there. Over billions of years, those craters have been quietly collecting whatever the solar system threw at them. The evidence built up slowly, and it's worth walking through because it's a good example of how a scientific conclusion actually forms. In 1994, a mission called Clementine bounced radar into the South Polar craters and got a return that was consistent with ice. It was also consistent with rough ground, and it was disputed immediately. In 1998, Lunar Prospector carried a neutron spectrometer. Hydrogen slows neutrons in a characteristic way, so a dip in the neutron signal indicates hydrogen below the surface. Lunar Prospector found strong hydrogen concentrations at both poles. Hydrogen is not proof of water, but it is a strong hint. In 2009, an instrument called the Moon Mineralogy Mapper, built by NASA's Jet Propulsion Laboratory, detected the spectral signature of water and hydroxyl molecules across wide areas of the lunar surface, not only at the poles. And then, on 9th October 2009, NASA did something direct. A mission called L-Cross steered a spent rocket stage weighing about 2.5 tons into Cabeus Crater, a permanently shadowed region near the South Pole, at around 5,600 miles per hour. A second spacecraft followed 4 minutes behind, flying through the debris plume and analyzing it before crashing itself. The plume contained water, roughly 5.5% of the ejected material by mass. It also contained carbon monoxide, ammonia, methane, mercury, and silver, which tells you these craters have been collecting a great deal more than water. Since then, in 2018, direct spectral confirmation of surface-exposed ice was published. In 2020, the airborne SOFIA telescope detected water molecules in sunlit terrain near Clavius Crater, which nobody expected at all. The question is no longer whether there is water, it is how much, in what form, and whether any of it can actually be dug up, because here's the difficulty, and this is where the phrase "most dangerous place on the moon" earns itself.
Imagine standing there. The sun is on the horizon and stays on the horizon. Every rock, every ridge, every rise in the ground throws a shadow miles long. And because there is no atmosphere, there is nothing to scatter light into those shadows. On Earth, a shadow at noon is still perfectly navigable because the sky itself is a light source. On the Moon, a shadow is absolute. It is not dim. It contains no information at all. So the terrain in front of you is a hard mosaic of blinding white and pure black with no gradient between them, and a boundary sweeps as you move. Now add the temperature. Stepping from sunlight into shadow at the pole can mean a swing of hundreds of degrees across a few feet. Machines are not fond of that. Batteries are not fond of that. Seals and lubricants and cameras all have opinions about it. Now add the dust from every landing, which in vacuum does not billow and settle. It travels in flat ballistic sheets at high speed and sandblasts anything nearby. And add the ground itself, which at the poles is ancient highland terrain, rough, boulder-strewn, and cut in places by those long thrust fault cliffs. Despite all of that, this is where everyone wants to go, and the reason is chemistry. Water is drinkable, water is breathable once you split it, and water split into hydrogen and oxygen is rocket propellant. Every pound of anything currently on the Moon was launched from Earth at enormous cost. If you can get propellant from the lunar surface instead, the arithmetic of everything beyond the Moon changes. The Moon stops being a destination and becomes a filling station. That is the actual strategic argument, and it is why the South Pole rather than the equator, and why now. There is a second kind of terrain at the pole, and it is the mirror image of the first. If a crater floor can be permanently dark, a crater rim can be almost permanently lit. Stand on high ground at the pole, and the sun circles you at eye level without ever setting. There are ridges near Shackleton that are in sunlight more than 80% of the year, with the dark gaps lasting only a few days. For a solar-powered base, that is close to ideal. Continuous power, no 2-week night to survive, and a permanently shadowed crater a short drive away. There is one further oddity about those ridges. Because the sun never rises high, a structure there would be lit from the side, permanently, and its own shadow would sweep slowly around it over the course of a month like the hand of a clock. None of this has been done yet, and the record so far is humbling. NASA spent years building a rover called Viper, designed to drive into the polar terrain and drill for ice directly. In 2024, with the vehicle largely assembled, the mission was cancelled on cost grounds, and there was a public argument about it that has not entirely finished. In March 2025, a commercial lander called Athena, built by Intuitive Machines, reached the South Polar region carrying a drill and a small hopping probe. It came down inside a crater, tipped over, and could not generate power. It lasted hours. The polar terrain has beaten every attempt to land precisely in it so far. That is not a reason to expect failure. It is a reason to understand why the schedules keep moving. Which brings us to where things currently stand. On the 1st of April 2026, 4 people launched from Kennedy Space Center on a mission called Artemis 2. Reed Wiseman, Victor Glover, and Christina Koch of NASA, and Jeremy Hansen of the Canadian Space Agency, who became the first person from outside the United States ever to fly to the Moon. They did not land. They flew a free return trajectory around the far side and came home, splashing down on the 10th of April. On the 6th of April, they reached 252,756 miles from Earth, which is farther than any human being has ever traveled. The record they broke was set by Apollo 13, and it had stood for 56 years. They also took photographs of the Earth from behind the Moon, which is a view that had not been captured by human hands since 1972. What comes next is less settled, and I want to be straight with you about that. The Artemis 3 crew was named on the 9th of June 2026. Randy Bresnik as commander, with Luca Palmito, Andre Douglas, and Frank Rubio. The target is 2027.
What that flight will actually do is currently in flux. NASA itself has mission descriptions having it landing crew near the South Pole. Recent reporting describes a flight profile focused on rendezvous and docking practice, with the landers being built by SpaceX and Blue Origin, with the landing itself depending on whether those vehicles are ready. Both things are being said publicly at the same time. The honest position is that the crew is named, the hardware is not finished, and the schedule has moved before. What is settled is where they're aiming. NASA has narrowed the whole South Polar region to 9 candidate landing areas, each containing several possible sites, chosen for a combination of near-continuous sunlight on high ground and a quick access to a shadowed crater nearby. Sun to live on, darkness to mine. So that's the state of it. A pole tilted just enough to hold shadows still. Craters holding 2 billion years of collected ice at temperatures colder than Pluto. 9 patches of ground, a named crew, unfinished hardware, and a plan. The visits, if they happen, will be brief. Everything human on the moon has been brief. The other thing that is happening there is not brief at all, and it hasn't paused once in 4.5 billion years.
An inch and a half a year. That is where we started, and it is where this ends, because it is the one thing about the moon that has never stopped and never will. Every night, the moon is slightly further away than it was the night before. The difference across a human lifetime is around 6 feet. Across all of recorded history, since the first cuneiform tablet was pressed into clay, it is roughly 1/4 mile. You cannot see it. No one has ever seen it. We only know because of a handful of mirrors left on the surface by men who are now mostly gone themselves, and because we have kept firing lasers at those mirrors for 57 years without stopping. The moon that the first humans looked up at 300,000 years ago was about 2.5 miles closer than the one outside your window. The moon that the dinosaurs saw was around 1,000 miles closer and noticeably larger in the sky. Which brings us to the coincidence. The sun is about 400 times wider than the moon. It is also about 400 times further away. Those two numbers have no reason whatsoever to match. They are not connected by any physical law. It is an accident of where things ended up. But because they match, the moon and the sun appear almost exactly the same size in our sky. And that is the only reason a total solar eclipse is possible. For a few minutes, the moon covers the sun exactly, and the corona comes out, and the temperature drops, and birds go quiet. No other planet in the solar system gets that. Mars has 2 moons, and both are far too small. The gas giants have moons that swamp the sun entirely and blot the corona out. Only here, only now. Now is the part that does not usually get said. As the moon retreats, it appears smaller. At some point, it will be too small to cover the sun completely, and totality will fail. It will not fail all at once, because both orbits are slightly elliptical. So for a long stretch, some eclipses will still just manage it, and others will not. The calculations, worked through most carefully by the Belgian astronomer Jean Mies, suggest that from around 620 million years from now, total eclipses become an intermittent thing. Present sometimes, absent for long stretches. And the genuinely final total eclipse, the last one that will ever occur on this planet, falls somewhere around 1.2 billion years from now. After that, forever, the moon will be a black disk with a ring of fire around it, and the corona will never be visible from the ground again. Nobody will be able to bring it back. There is no mechanism that reverses this. There is a theoretical endpoint to the whole process, and it's worth knowing that we never reach it. If the system were left alone indefinitely, the Earth's rotation would keep slowing, and the moon would keep climbing until the two locked to each other.
The Earth would turn once every 47 days or so, and the Moon would hang motionless in the sky above one hemisphere, permanently invisible from the other. That would take something like 50 billion years. The Sun will have ended the arrangement long before then. In roughly 5 billion years, it will swell into a red giant, and whatever happens to the Earth and the Moon at that point, it will not involve either of them continuing quietly as they are. So the departure never finishes. The Moon simply keeps leaving until there's nothing left to leave. Which puts everything you've heard tonight in a particular light. The Moon was born in a collision, drowned in liquid rock, beaten half to death, flooded with lava, and then left alone for 3 billion years in complete silence. 12 people visited it during a very short stretch of the 20th century and picked up 842 pounds of it. And that's where nearly everything we know came from. And the version of it that we happen to have, the one that is exactly the right size to cover the Sun, the one that makes tides and steadies our seasons and gives us the word month, is a temporary configuration that we arrived in the middle of. Every generation that has ever lived has looked up at a slightly different moon, and not one of them could tell. The change is too slow for a life, too slow for a civilization, and almost too slow for a species. It's only visible from the outside, in the arithmetic, and we only have the arithmetic about a century. We are the first people who have ever known that the Moon is leaving. That's a strange thing to be the first at. The footprints will fade in a few million years. The mirrors will keep working for a great deal longer because nothing there can break them. And the Moon will keep going, an inch and a half at a time, whether or not anyone is left to measure it. That's the complete history of the Moon as far as we currently have it. Sleep well. Somewhere above you, it is still moving away.